Hey there! In this video, we're gonna build a complete IoT applications to monitor plants. We'll start from scratch by creating our own custom sensor that can measure soil moisture, air temperature, and humidity. To bring it all together, we'll be using our trusty ESP32 along with a LoRa module to enable long-range wired communications. We'll walk through setting up the gateway and configuring LoRaWAN to make data transmission more efficient and reliable. Then, we'll connect everything to TagoIO, where we will build a real-time dashboard to visualize the data from our sensors. This is not just a fun DIY project, it's also a great starting point if you are developing solutions for smart agriculture or looking to dive deeper into IoT technologies. If that sounds exciting, let's jump right in and get started. In this project, we are using a thin node gateway generously provided by our friends at Elecrow. So this gateway supports multiple connection options including Wi-Fi and Ethernet, offering a coverage range of 5 to 10 kilometers, and it operates on popular LoRaWAN frequency bands such as EU868 and US915, and one of the best features of the thin node is its simple setup process. So with just a few clicks, you will have your gateway up and running. A big thanks to Elecrow for providing us with this gateway and for supporting our channel. Alright, so let's go through how we will build our IoT solution from sensors to the final applications. So the first step, we will create our own device using these two sensors, the HW390 capacity sensors to measure soil moisture, and also we are going to use the DHT11 to measure ambient temperature and humidity. Both sensors will be managed by our ESP32 LoRa microcontroller, and our device will transmit data via LoRa to a thin node gateway, which will handle the information and connect it to the internet. And from there, the gateway will forward the data to TTS, the thin stack network, through LoRaWAN. Once the data is on the TTS, the LoRaWAN network server, we will integrate it with TagoIO to create interactive dashboards and visualize our sensor readings. To achieve this integration, we will configure a webhook which will automatically forward all the data from TTS to TagoIO. Well, we will use the free tier accounts for both the TTS and TagoIO, and all the hardware components are widely available online, so making them easy to find or to source. Alright, so to get started, you will need to create an account on the ThineStat, the free versions, so which allow you to use 10 devices and 10 gateways on the ThineStat cloud. And the sign up process is super easy. You just need to visit the documentation and follow these steps. It's quick and simple, and you will need also a credit card, yes, to complete the registration. So I believe you can do it by yourself. Okay, next, the following step is to create a gateway in TTS. So for that, we go to the gateway section here, click on register gateway, and then we will need to fill in the required fields. For example, here I will put any value in gateway EUI, and then you can put, for example, gateway ID. In this I will put gateway name, and here you need to choose the frequency plan. In my case is 915, and then click on register gateway. Oh, sorry, gateway ID. Okay. So in my case, I already had my gateway registered, which is this one, Signal A3. And if you go to the general settings, you will find the gateway GUI and also the gateway server address. So these two data is required if you wanted to configure your gateway physically. So in my case, I am using the signal gateway, and here are the sections that say LoRa gateway. If we go to these sections, you will need to configure the global parameters. For example, the LoRa interface, I am using Ethernet. The frequency plan, I am using US 915, and the LoRa mode packet forward. And well, this is the fields that I was talking. And this is the gateway EUI that need to match with the TTS from here, and also the server address that is the same from here. Alright, so once we have our gateway connected to TTS, the next step is to create an application. And to do this, we are going to go to application section here, click on add applications, and then we need to fill in these required fields: application ID, application name, and descriptions. And once you create an application, it will appear something like this. For example, I create an application called MirrorTech app, and then here we will need to create an end device. So we are going to go to end device, and then I will register a new device. Okay, once we are here, we need to select the input method. I will select the second options, enter a device specifics manually, and I will choose the frequency plan. In my case, is the US 915. We need to select the LoRaWAN version. I will select the 1.0.2, and also the regional parameters. I will select the revision B. So in the provision informations, we need to use we need to select our join EUI. I will put a random value just to make an example. For example, this, and click on confirm. You can then generate a dev UI and also generate an app key. And you need to complete the end device ID. I will put, I don't know, ESP32 number 2. Okay, and then click on register end devices. Okay, so once we have our end device configured in our TTS, the next step is configure or programming our ESP32 using Arduino IDE. So let's open Arduino IDE, and then we will use the example that Helte provide us to make LoRaWAN communication. Let me open this code, and as you can see here, this is a code by HealthTech Automations that is a LoRaWAN communication example. So we need to change this dev EUI, app EUI, and app key for hours. Let me update it. Here is P3 define7E TA 003F E7, and then update the app EUI. I will put AA, 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 and then the last one is 33, and also update the app key. So let me copy in this format, and here let me delete this and copy ours. Okay, also you will need to select your LoRaWAN regions. In my example is US 915, but probably you are using another region. So the only thing that this code does is connected to LoRaWAN server and then sending these informations that is sending 0, 1, 2, and 3. So let's test it. Okay, so let's open our serial monitor. Okay, we are sending some informations. As you can see here in our serial monitor, we got the confirm upload sending, and also in our TTS is showing the last activity. So if you go to TTS, we can see what data is sending from our device. For example, if you go to the live data section here, you will see all the live stream data. For example, our device is only sending 00, 01, 02, and 03. You can see here all the packet that is coming from our ESP32 device. Alright, so now that we know how to connect our ESP32 to TTS, so we are going to use this code to continue with our project. So this code reads the temperature and humidity values from our sensors and then send them to TTS. So I will leave this code in the video descriptions, and of course you have to take account that you need to change the dev EUI, the app EUI, and also the app key. Alright guys, let's see which elements we are going to use in our project. So we start with our capacity moisture sensor, the HW390. As its name suggests, this sensor measures soil moisture using a capacity method, which is much better than a resistive method used by other sensors, like this one for example. This sensor is good, but it deteriorates very quickly. The next element we are going to use is this temperature and humidity sensor, the DHT11. So this sensor will help us measure ambient temperature and humidity. And the next one is our ESP32 LoRa. This will be our microcontroller. So the good thing about this design is that it already includes an integrated OLED display and a LoRa module. This is the healthier version number 3. It has a battery socket, use USB Type-C, and also comes with a small antenna, which will be very useful. And then we will also use the case design for this model. This case will be very helpful to provide more protections to our device and add more rigidity. Okay, so what we are going to do now is solder the pins to our ESP32 so we can make our connections. Alright, so now that we have our ESP32 ready, we are going to connect our sensors and the battery. So the wiring diagram is very simple. We just need to power the sensors with 3.3 volts, and the data wire of our DHT11 goes to pin number 5, and the data wire of our ESW390 goes to pin number 3. Alright, so now that everything is connected, we will use our 3.7 volts lithium battery. The one I have is 1400 milliamps hours, and it will work great for our device. Alright, so now that our IoT device is up and running, let's test our moisture sensor. I'm just going to touch the capacity part of the sensor with my finger. Now the relative moisture level has increased from 8% to 91%. So now let's test the temperature and humidity sensor. The temperature and humidity increase, but the response is a bit slow. However, our sensor is definitely ready and fully functional for assembly. So let's get to it. Okay, so for the creation of our device case, what I'm going to do is module in 3D the parts we will use, such as our sensors, the ESP32, and the battery. This will help us with the final assembly and allow us to see any interference between the parts. Here is the first 3D design of our case. While it is a good starting point, I'm noticed some areas for improvement. For instance, we could make the upper case more rigid and redesign the back cover to ensure a more secure attachment. Overall, it's a solid first draft. Now we can focus on refining it further. I think our device design is much better now. We made it more compact by reducing some spaces and made the cover stronger. So as you can see in the sectional view, there are no interference in our parts, and I think the space inside will be useful for placing the cables in our temperature sensor. So now the design is ready, we can start printing.